Okay, welcome back everybody. This is our second lecture in our contaminant transport chapter, and today we will be talking about the solutions to the advection dispersion equation that we saw last time. So we saw the derivation of them, the differential form at the end of the chapter last time, and now today we want to look at the solutions, because what we want to know is concentration at some place and time, and so we're interested in solutions to the differential equation, not the differential per se. Okay, so again, from last time you'll remember what the advection dispersion equation looks like, and you have it here on the left hand side. If I get my pen on, right here, right, this is your advection. So the advection part is the velocity. The dispersion part, and again here is just in one dimension, right, just for simplicity. You have a dispersion coefficient, a velocity, and this is the differential equation for the transport of the contaminant. Here's the 2D version where you have a longitudinal and a transverse dispersion coefficient. Of course, if you have a well, for example, or sometimes you'd be interested in radial coordinates, which again you can transform that 2D into radial like we did in the last lectures and the last chapter, I should say. But again, what we want is C at some place and time. Let's see how we get there. There's three methods that we will detail a little bit. We'll detail each of them some today. And again, this is going back to some of the previous lectures in previous chapters, especially in chapter 4 when we did the flow equations, and we saw some analytical solutions and some numerical solutions. And here today what I'll introduce that I haven't really talked about much yet is that particle tracking solutions. So very quickly, right, analytical solutions are just mathematical solutions, meaning you take the differential equation, you actually solve, do the math, either on a piece of paper, or you use Mathematica, Maple, or any other symbolic math software, and then you can find the solution to the equation. And this is the example here. I'll detail this in a minute, but this is basically a Gaussian. So the solution to the differential equation, the concentration over in space and time is a Gaussian. And this is an illustration here at the bottom where you can see the diffusion of that plume basically in the x-axis, right, over time. So after some time, this is what you would see, that red line, and then after some more time, you'd see that blue line, and you can see how it diffuses out. Here in the middle, the numerical solution. So again, we've talked about those before. You might remember this from our FlowNet and finite difference solutions that we've done before. So here we use the same tricks basically to find difference equations for these differential equations. And as we've done before, we can find basically the solution at some later time step or some further spatial extent, right? We can find a solution by using those difference equations. And here at the bottom is an illustration. You can see those little squares reminiscent of the GMS squares, right? There's a grid here. So we solve the equations on some sort of a grid, basically on some sort of finite difference, finite element sort of a scheme. And then finally, today we introduce particle tracking, which is basically a stochastic method. So we take random numbers that represent the Gaussian solution, essentially, and then we'll see how we can use a bunch of particles to follow them in a flow field that we have. Here is again a GMS tutorial that you did before, and you can see here we put a number of particles in that injection well, or simulating that contamination at this point that we did at the beginning of the wells chapter. And you can see that you can track the flow path basically of each particle in that flow field, in that aquifer, and that's pretty much what particle tracking does. Okay, so the first one is analytical solutions, right? Again, the Gaussian solution here is C of x and t is m over 2 square root of pi dt exponential minus x minus vt over 4 squared over 4 dt. Okay, so this solution here, you should really maybe not memorize, but remember that this is a Gaussian. That's really the important part. Again, this is the fundamental solution for a pulse, meaning that the initial condition here is basically a pulse meaning like a Dirac delta function or some sort of discrete pulse. So you inject, like, let's say you drop a bucket of something, and then that's it. There's no more source. That's a pulse. Now, over time, again, you can see how it diffuses away from the origin. In this case, it stays at x equals 0, and the reason for that is because we assume v equals 0. So this is basically the same as solving the diffusion equation, except now your dispersion coefficient is actually dispersion, right? So if v equals 0, it stays in place. If we had some velocity, in the flow field, if it was going this way, then of course you would have your, red line here, some place later, and then of course your blue line would be even later, right? So that's just the effect of v. Now another analytical solution that you can get for the math for a different initial boundary value problem, or different initial conditions, is illustrated here on the right, and that would be a condition where now you have a source basically on the right hand side here, right? So this is your initial condition at t equals 0. Right, so at t equals 0, so imagine you have again a landfill, right? And now you have a leak, right? So originally you had some barrier that would prevent, the contact between your clean groundwater here and your dirty groundwater here, right? And now imagine you have a leak in that barrier at some time t equals 0, right? So now those two waters are in contact. Now this source here is going to continue spilling into that clean water, and then vice versa, right? The clean water, if you will, is spilling on the dirty water. So at the interface here, we get that, again, that spreading or that diffusion of, basically dirty water here and clean water here. So you have that, after some time, right, you have that smoothing over time, and those two concentrations, eventually would become the same, throughout the domain. So at the interface here, this is an analytical solution that we can find in math. Again, this is a solution with an error function. I'm not going to detail here what that is, but this is just a known function, so you can actually, plug this in a calculator and find your solution, so your concentration at some point in space and time, according to this solution. Now, one thing to note here, the real fundamental solution is this one here, because if you take a bunch of pulses, and we'll see this in a second, you can actually recover the error function solution without using it. So we can just use a bunch of pulses to mimic most situations we might have in real life. Okay, so first, important characteristics of the fundamental solution. Again, the fundamental solution is up here on the right, and this would be your Gaussian solution. So one of their characteristics is the peak, and the peak is here, that little red dot that we have here. This is for a Gaussian, you may or may not remember this, but for a Gaussian, the peak is given by this, right? So the maximum of the curve is given by this first term here before the exponential. And again, this is the mass over the square root of 4 pi dt. So you can see that the mass, of course, is going to, influence the peak, and then the peak is going to be inversely proportional to time and dispersion, meaning that the more dispersion you have, the less the peak is, because again, the mass is spreading, more and more. So if it's spreading faster, now you get, for that same time, you get a fatter curve, and because the mass is, constant, always mass balancing, right? That would look like this, so the peak would be smaller if dispersion was faster. And then time, we already saw it before, right? Again, as time goes on, dispersion, does its thing. So the whole curve is spreading more and more and more, so that by again mass balance, the peak is going down and down and down. So okay, time and dispersion, reduce the peak, and of course mass increases the peak. But this gives you the peak of the Gaussian. Now another important thing, of course, is mass. I already talked about this, but the mass is right here, so this is the only place you see the mass. So the mass, you can calculate the mass when you have a Gaussian by taking the integral under the curve. So if you will, again, this is called the zeroth moment for those of you who were in 547, right? Whoa, what did I do? Okay. So if we take the integral under these curves here, let me clean it up, right? So if we Oh, I see what I did. I need to get back here. Okay. Huh. Oh well. I guess I have to live with that. Oh, I see. Okay. All right. Sorry about that. Okay, 1, 2, 3. So for the mass, we can take the integral under the curve here, and that will give you the mass. So this is equals to integral of cx t in space dx. All right, so this is basically the zeroth moment, but if you take, if you sum up all those points in space, again, this is x here on the x-axis, and this is c of x at some time, then you can integrate that and get the mass. So that's one thing. And finally, very important for this course is the standard deviation or the variance. Let me try and get a little here. Oh, maybe that's too much. Sorry, I just saw that it was really dark in there. Okay, maybe that's better. Okay, so the standard deviation, sigma, equals square root of 2dt for this solution here. Or another way to write this, right, is that the sigma square, the variance, is 2dt. And you can see here that 2dt is here, right? So 4dt, that's 2 times the variance, right? So it's square root of 2 pi 2dt, right? This is equals 2 pi 2dt, right? So this is 2 pi the variance, sigma squared. Right, 2dt is the variance. Meaning that if we have a distribution of concentration, we can just measure the variance of it and find the dispersion coefficient. So in practice for aquifers especially, that's very important because we don't know what dispersion is a priori. I explained the whole tortuosity business in the last lecture, so it's very difficult to a priori know what dispersion is. Basically, there's no way to do that. So the practical way we actually calculate dispersion in an aquifer is to measure a tracer. So we can do, you can do tracer tests. You can put some salts in there or, something that is not dangerous for the environment, obviously. Release a pulse, measure it after some time, and then calculate the variance and backtrack, knowing the variance, knowing the time, the only unknown would be the dispersion, and that's how you calculate it. So it's a very handy, simple way to find the dispersion coefficient in a formation. Now the limitation of the analytical solutions, the main one probably is that homogeneity, right? So you can see those equations are very simple. We have not talked about hydraulic conductivity, for example. So if you have a heterogeneous media with different types of rocks or different hydraulic conductivities, which is typical, typically hydraulic conductivity is not constant in space, right? So then you can't really integrate that in your methods of solution. You have to go with the numerical solutions. Again, simple geometry. So we've seen a couple of initial boundary value problems before, right? Solutions. But if your geometries are complicated, it becomes very hard to find, mathematical solutions for those kinds of boundary or geometries. So that's what we use numerical solutions for. One last thing on analytical solution before I move on to numerical solutions. The principle of superposition. So again, we've done that for wells before, right? So when you have a well field, when you have multiple wells, because they're all independent and things are linear, we can just add them up. Same thing here, right? So if you have the solution of 3 different pulses, like in that first figure, and again, those of you in 547 will recognize some of those figures here. But let's say we have 3 different sources, right? So 3 different buckets of contaminant released at 3 different places, right? We can calculate analytically, we can use our Gaussian solution, right? That blue line and then that, whatever that is, orange line here and that yellow line here, independently, right? So we can calculate the solution for each of those sources or each of those pulses, and then we can just sum them up to get that dashed red lines, which is the solution for all 3 together. Okay, so really important. So if you have multiple things, you can just calculate them independently and sum them up, just like we did for the wells. Now, a corollary to that, again, like we did before for the wells, is boundaries, right? So if we have an impervious boundary here, that black line, we can actually simulate that boundary with a source, an image source solution, right? Just like we did before. So if we want to know what the behavior of the contamination is going to be near the boundary, what we do is we add here, we add here, well, I don't know why this is doing this, okay. Somehow there's something interfering with my Bluetooth here. But anyway, so away from that boundary, so this is our original contamination. I don't know why this is jumpy. Why is it jumpy? Okay. So this is where the original pulse is, and there is a boundary. So now we put an equivalent pulse, the same distance on the other side of the boundary, just like we did a pumping well, right, on the other side of the boundary. And now we can take those two solutions and sum them up. So if we look at that magenta after, 3 time steps here, or at the latest time, like that magenta line, you can see the first solution is that solid magenta. The image solution is that dashed line magenta. And if you sum those two magenta lines, so here, for example, this plus this is this point here, right? And then again, dashed line plus solid line is this point here. So the little dots here are the solution, near the boundary. And you can see that's quite a bit of difference right here, right? Between the, no image with the image. So the boundaries we can treat as multiple sources, superposition. And then finally, the more important part here, and I'm not going to give you the equations for that. Those of you who are taking 4482, I believe maybe a couple of you are, the seniors, or if you've taken any kind of hydrology course before, you've probably seen the convolution problem. And convolution is basically the same as described before. It's pretty much a superposition, right, in space or in time. So basically you take a whole bunch of little pulses and you sum them up together. That's really what convolutions do, right? You just like run those two functions together. So your initial condition need not be, a perfect pulse or a perfect square, right? Your initial condition could be, some function in space that is complicated like this. But then if you know your pulse solution, so your Gaussian, this is your pulse. Well, this is supposed to be a Gaussian. I don't know why my pen is acting up today. It's just doing its own thing. But anyway, so if you know the pulse solution, this would be the solution, the Gaussian solution. You convolve this pulse solution with your initial condition, which can be a, arbitrary function, and then you get the solution for that. So just by using convolution, you can actually get some pretty complicated, initial conditions or even boundaries, included analytically. And again, here you can see those blue. The blue line is just a superposition of individual pulses, right? And the red dashed line is basically doing the convolution of the multiple pulses as initial condition, with a single response, basically, or the pulse response, the analytical Gaussian solution for each individual pulse. So again, if you convolve this initial pulse with the multiple buckets that we threw here, then we get the exact same solution, whether it's a superposition or a convolution is the same. And just to wrap up this analytical part, I told you before, right, for the error function solution, you have an analytical solution that I described before, which is that red line, so you can do the analytical, the mathematical stuff. But you can also take, a whole bunch of pulses. So this square here, right, you can imagine that this is basically just like having a bunch of little pulses. And again, I'm sorry that my pen is acting up today, but so imagine this square, right, as a bunch of little discrete pulses, right? Now each of those can be, again, one little Gaussian, solution, and then you sum them all up, you convolve them together, and you end up with the exact same solution. You can see that dashed blue, the dashed blue line here is the convolution solution. So again, by doing convolutions, we can actually, find some somewhat fancy analytical ways to solve problems. Okay. Finally getting to the numerical, right? So I said that the analytical, the problem is, can only treat some simple problems that are not very realistic typically, right? So what we'd like to do is typically is model a contamination in a real aquifer that may have, multiple layers of different hydraulic conductivity or different material, complex geometry. So all those things basically we'll have to use a numerical numerical model to do that. Again, just a reminder here. Excuse me. Just a reminder here that this is the equation you're trying to solve. And if you remember from our FlowNet chapter, right, we saw how this works. So this is a figure that we used, to explain the difference between a differential, right, the tangent to a curve, which is the definition of the differential, and the finite difference approximation, which says, if you take some small space around, you can basically find the value. Okay. Again, here are the three main results from that lecture, where the first spatial differential can be, represented as, this function after, function before, divided by 2 times the delta x, right? So you have the delta x down here. The second derivative is given by this expression here, in finite difference form, and then the time differential is given by this expression here. And you can see, obviously, it doesn't matter if it's time or space, it's the same expression, but you can approximate that by ft plus 1 minus ft divided by delta t. Instead of taking the after and before, you can just take the after and here, right, divided by delta t. So again, I invite you to go back to the notes on this if this is a bit advanced. But now we have the three expressions, and you can recognize those from our advection dispersion equation, right? So we have dc dt, right? So we need that. This is this, right? We have dc dx here, which is our advective term, which is here. And we have the second differential, d squared c dy squared, or dx squared, which is here. So now we have everything we need, right? We can just replace those differential by their equivalent finite difference expression. And then finally arrive to the solution. Again, remember that our goal here is to find c at x and t, right? Which is given by here in ij. So this is a 2D problem solution. So at the concentration at t plus 1, so in the future, in the next time step, at some place xy or ij is given by the concentration here and now, so at t, right? Time is now. We're looking at, the solution in the future at that same place, plus, some coefficient here that, the dispersion coefficient, the delta t, right? The time step, delta x, which is the spatial step, and then again the 4 neighbors, basically. And you remember that from before, right? Basically, when we do simple 2D finite difference, we take the 4 neighboring cells to find the value in this cell. So this is, again, the finite difference equivalent for a simple advection dispersion equation solution. Now, in practice, what does that do, right? Well, this is an example, right? So this is, again, our differential equation. We use the finite difference approximation in Excel or in Matlab. This is Matlab, obviously. And we can find a 2D, plot. And again, you can see here all those pixels represent little squares, right? Little cells, just like we've done in Excel before. And we compute, the concentration values over time, by just running iterative solutions like we've done before, using those solutions. Again, the big advantage here is that you can use any sort of domain that you want, right? So let's say you had a geometry that was like this, right? You can just treat that just as simple as before. Let's say you had now some different hydraulic conductivity cells, and again, I invite you to go back to our FlowNet and the discussion there, because I didn't include it in this lecture, but you can easily include the velocity here. You can find the different velocities everywhere from the flow equations, right? And once you have the velocity everywhere, then you can plug it in your finite difference solution. So each cell doesn't have to be the same velocity, right? You can have different RC fluxes at different places. So anyways, your domain can be arbitrarily complex, and you can just run the finite difference solution and find the behavior of the plume around those complicated regions that you couldn't do analytically. Okay, finally, a few words on particle tracking, right? So again, this is the GMS tutorial that you did before. We start with our ADE equation up here. Whoops, Same equation as before, and I'll show a very simple example for the basic process of using particle tracking to solve equations. So there's two things we need to worry about, right, when we do advection dispersion, is advection and dispersion. Now, if we think of velocity, right, advection, if we think of velocity as the mean of a distribution divided by delta time, remember velocity is length per time, right? So if we think of, and this is units, or dimension, I should say. Okay, the dimension is length per time. So if we think of the position of a plume, right, the mean position in x after some time t, so let's say we start here, and then after some time we're, somewhere here, and this is the mean position, so this is the distance traveled, L or X or whatever you want to call it, right? So we've traveled some distance L downstream or downflow in a time, whatever. So let's say we traveled 1 meter in 10 seconds, right? Our velocity is 1/10, 1/10 meters per second. So really the velocity, if you will, is the mean position of that plume, right? So if we have particles everywhere around here, but the mean is here, we can calculate that velocity. Dispersion is the same idea. I already told you before, dispersion is variance, right, equals 2dt, which is the same thing. Now, if you think about this, right, that means that the dispersion is just basically an expression of the variance of that distribution of particles that I have here, right? So if I know where all my particles are, right, I can calculate the variance here, the variance of that plume, like I said before, this is literally how we do it. And then from the variance, I know the dispersion. Okay, well, now we have everything we need, right? So basically what I'm saying is all we need is a distribution, a Gaussian distribution with a mean and a variance, right? And we can pick random numbers from that distribution and simulate the flow. Okay, so again, the process here on the right-hand side, right, is you take a normal distribution of known mean and variance, because again, V and D are basically the mean and the variance. You take random numbers from that, and then you move particles randomly with these values, right? So if you have a particle, you take, the velocity is again 1/10 meters per second, so let's say 10 centimeters per second. So you move that particle 10 centimeters every second, right? This particle is going to move 10 centimeters every second, cluck, 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 regularly. Now, the problem with, again, dispersion is that it adds, random velocities around the velocity, and that's what you do here. So instead of having just the mean, now we can take random numbers around that mean. So maybe this particle, instead of moving 10 centimeters, moved 8 in the first step, right? Because randomly, you got a little before the mean. But maybe on the next step, she moved, 20 centimeters, and now she's here. And then the next one, she moved 3 centimeters, and then the next one is 5 centimeters, so on and so forth, right? So instead of moving cluck, 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 cluck with velocity, now it's moving velocity plus or minus some random component that is the dispersion, the variance of that. Now, if you have a bunch of particles, again, you can just average over and backtrack V and D. So let's do an example here. So this is the pseudocode in Matlab, and I'll show you the real code in the next slide. We take a normal distribution, normal as in Gaussian, with a known mean and variance. Oops, excuse me. Which means, let me get my pen here. So here the mean is mu equals 0, meaning we're doing the diffusion equation. Basically, we're not letting it drift, so the velocity is 0. And the sigma, so the standard deviation, is 0.5. Okay, so now we have our distribution. Again, this is pseudocode in Matlab, and I'll show you the complete code running in the next slide. Then we take a random number from that distribution, so I call this shift, and I take normal distributed random number. This is again a Matlab function that does it for you, mean mu, standard deviation sigma, and I take n numbers, and this is just one column, right? This is Matlab, so it's row, column, so n rows, one column, so n numbers from this distribution. N would be the number of particles that you're simulating, if you will. Then we move the particles, for each time step. So for time t plus 1, the new position x is the old position x plus the shift that we just picked. Okay, so so on and so forth, right? You do this a bunch of times for whatever time steps you want to do. So if you want to do 1,000, 1,000 steps, then you do this 1,000 times, right, on a loop, for example. And then finally, you just plot the positions, and you can do histograms, or you can do, the mean position. So in practice, what does it do? And again, here on the left, you have the code that will be on your code folder in this chapter. And then here on the right, we have, sorry, I'm trying to get out of my pen here. And then here on the right, we have the movie that this code is doing. And you can see here, this is almost from the beginning, not quite. Oh, yeah, this movie didn't work quite as expected. But anyways, so at the beginning here, if I restart it, you can see here the particles sort of moving away. And again, I'm sorry, I just have the last few frames of the particle tracking actually moving. But you can see how they're spreading around. And then this is the histogram of the last position, so the last snapshot that you just saw, the little particles moving. If you take a histogram of it, right, this is their mean position. So you can see the mean here is still 0, right? Because again, we assign a velocity of 0, but the standard deviation or the variance here is represented by this spread here. Okay. If we look at sigma, and again, sigma is the standard deviation is 1.67. So if we take sigma squared, it's going to be 2.5, excuse me, 2.5, and then time is 10, so sigma squared over 10 equals 0.25, right? Times 2, remember, times 2 times t, sigma squared over 2t equals d, equals 0.5, which is here. This is what we used to get our, here, our dispersion coefficient, right? So everything is self-consistent, if you will. So again, you have the code here on the left, you have the result, the overall average at the fourth step from the line before, and again, this orange line is basically the analytical solution or the equivalent analytical solution, and the histogram here is the position of our random walkers, in space. So again, this random walk method basically allows you to solve these transport equations. Okay, and finally to conclude here, these are two different figures that show that those three solutions, so analytical, numerical, and particle tracking, basically are the same. They're good for different things, but in the end, for simple cases that you can do analytically, they solve the same equation. So their result is just the solution of that equation. So hopefully they should be the same, right? And you can see here on the left, you have in yellow is the particle tracking that I just showed. In red is a 1D analytical, and in blue is actually a 2D analytical. So I don't have the final difference on this plot, but you can just see that they do the same thing basically. On the right-hand side here is another an Excel interface. So there is some Visual Basic code basically running in the macro. So this is again in your code folder under diffusion codes.xlsm because of the macros, and you can go into your macro editor into the Visual Basic editor. If you don't know how to do this, this is in your developer, in the developer menu, and then in there you can go to the macros, edit them, and you can see the code. I'll upload that code independently too, so you can see that you can run this interface and it does an analytical solution, a numerical solution based on finite difference, and a random walk solution, which is what we just did, but all coded up in Excel for simplicity. So I put that in your folders. So again, 3 different methods of solution. Mostly what's important to remember is the pulse solution, the fundamental solution. So from a pulse to a Gaussian, because from the Gaussian by convolution, you can basically backtrack everything else. Now the other thing is that's important is to understand the numerical solutions, because these allow you to solve much more complicated domains, and that's basically what, again, GMS does, right, is the mod flow code, which is a finite difference code from the USGS that solves exactly those equations, right, the flow equations, and on top of that, the solute transport equations that we're analyzing now. Okay, I will post a little activity on this lecture, and I will see you on Monday. So on Monday we will move on to, if I can remember, reactive transport, right? So on Monday we'll do reactive transport, meaning for now we've basically seen flow equation, so concentration that moves with the flow. But what happens if you have a reactive contaminant, so something that sticks to the particles in the soil, for example, or something that is used by bacteria, such as nitrate, for example. If there's denitrification, right, the nitrate disappears, and now we have to account for the reaction. So we'll delve into the chemistry a little more on Monday. All right, thank you.